Hello, one and all. Welcome to problem set 7.1 for those of you that need a little explanation on how to do these problems. All right, so here's our first problem, 7.10. Notice how this is different than what we did in chapter 6. Chapter 6, we were given a lot of two-way tables, right? But notice this is a probability table, right? We have the discrete outcomes and then the assigned probabilities here. So it's a little bit different type of table, okay? Right? Everything in the body of the table is a probability as opposed to a raw count. All right, question A. Verify that each of these is a legitimate discrete probability distribution function. Remember, that means that every entry must be between 0 and 1, and the sum of all the entries must equal exactly 1. So to verify it, I first look and say, okay, all of those entries are between 0 and 1. Now I just have to add them up and confirm that it adds up to exactly 1. Okay. Okay, and sure enough, the household probability has a sum of exactly 1. Now the family probability. Also has a sum of exactly 1. So there we go. We've just verified that each of those are legitimate probability distributions. All right, letter B, make probability histograms for each distribution using the same scales. Okay. So, zoom in a bit there. It's hard to fit this. All right, so my first distribution goes from 1 to 7. And 32% is the category with the most. So let's call that, I don't know, right about there. We'll say that's 30. All right, let's see. One person has a probability of 0.25. So something like that. Two people, that's our 32%. Three people, 17. Four people, 15. Five people is 7. 6 people is 3, and 7 people, 1%. Okay, this is number of people. And this is probability. And this is for households. Okay, now do the same thing for our family. Now, of course, a household, you can have a household of 1, right? You're just a single person living on your own, but they don't consider that a family. So when I do my family, I'll still put 1 here, but if you look at the problem, that it's 0% probability because you're not considered a family of 1. So let's see, 30%. Okay, so on the family probability, you'll see that 42% of our families are just 2 people. And then 23%, something like that. 21%, 9%, 3%, and 2%. And this is family. Okay, so there you go. You can see the two distributions, and then it does a little follow-up. What's the most important difference? Well, the fact that you can have a household of one person, but you can't have a family of one person. There's your big difference, right? Other than that, they're both right skewed. Yeah. Okay, moving on. Next question. Oh, whoops, I labeled that 7.11. That was actually 7.10. Sorry about that. All right, next question, 7.11. Choose an American household at random, so one of these. Okay, so top row. And we're going to call that random variable y, the number of persons living in that household. Okay. Part A, express more than one person lives in this household in terms of y. Okay, so that's probability that y is greater than 1. Okay. What's the probability of this event? Okay, well, looking at our distribution of household residents, you can see that it's going to be 75%, right? You can find the sum of all those, or you can do the simple complement, right? 1 minus 0.25, that's the way I would do it. So 75%. All right, part B. What's the probability we have more than 2 and less than or equal to 4 people in the household? Okay, so that means 3 or 4, basically. Write that down. Okay, so this is equivalent, since it's a discrete distribution, right? Can't have fractional family members or household members. 3 or 4 works for this. 2 is not included. So going back, that's 0.17 plus 0.15, or in other words, 0.32. Okay. And part C, what's the probability that y does not equal 2? So a household with any number of people other than 2. So again, the easy way to do that would be use the complement, right? So I would just do 1 minus 0.32 is the fastest way to do it, right? The other way to do it is 0.25 plus 0.17 plus all those, right? But using the complement's probably faster. So 1 minus, and there we go. The probability the household size is not 2, 68%. Okay, next question. Now we have a probability distribution for the number of, I'm going to say vehicles, because it's cars, SUVs, light trucks, in a household. And question A, verify it's legitimate. Okay, so again, all entries are between 0 and 1, and then I just have to add them up, and they, as long as they sum to exactly 1, it's legitimate. So let's see, 0.09. 6 plus 0.35 plus 0.13 plus 0.05 plus 0.12. And sure enough, equals exactly 1. So we verified that's a legitimate probability distribution. All right, B. Say in words what the event X is greater than or equal to 1 is. Okay, well, that means the household has at least one vehicle, right? Guess you could say motorized vehicle, right? Okay. Oh, find the probability X is greater than or equal to 1. So again, I could add all those up, but I'm going to use the complement, right? 1 minus 0.09 is the faster way to do this. Okay, so 91% of households have at least one vehicle, motorized vehicle. Okay, part C. A housing company builds houses with 2-car garages. That's quite common. What percent of households have more cars than the garage can hold? Okay, so we were trying to find the probability. Excuse me. That our households have 3 or more cars, right? Because 2-car garages can't hold 3 cars. So that's the sum of those 3 entries. So 0.13 plus 5 plus 2, that's what, 20%. Okay, hopefully that's pretty straightforward. All right, we're skipping 13. Moving on to number 14. Okay, so they have 2 balanced, so in other words, all the sides are equally likely to happen, 6-sided dice. One standard, meaning numbers 1 through 6. The other is a non-standard die. 3 of the sides are labeled 0, and 3 of the sides are labeled 6. Find the probability distribution for the total number of spots when we roll these 2 dice. Okay. So, this is kind of interesting. You could just do a sample space, or, yeah, you probably don't want to do a tree diagram. So I'll just kind of make like a chart here, listing everything out. So we could get on one of the dice, 1, 2, 3, 4, 5, 6. On the other die, it's 0, 0, 0, 6, 6, 6. So right here, this entry would be a 0 and a 1, so the sum is 1. Like that. Okay. Here's a 2 and a 0, so 2, 3, 0, 3, so on and so forth, right? Okay, here's 7, 8, 9, 10, 11, 12. And there we go. So writing it like this, we can see I have 36 outcomes, but notice they're coming in sets of 3, right? So each outcome, we can get anywhere from 1 to 12, just like if we rolled standard dice. But with standard dice, actually, back up. With standard dice, you can't get 1 to 12, right? You can get between 2 and 12. So that's different. And then also the distribution with standard dice is getting, say, 2 is a 1 in 36 shot. Getting 12 is a 1 in 36 shot. But with these dice, each of these is equally likely. So that's kind of interesting, right? We can get anywhere from 1 to 12, and each one has an equal chance of occurrence. So a 1 in 12 chance of occurrence. Pretty cool. Okay, moving on. Next question. All right, so anybody who goes to college is just thrown in with they completed high school, and the study stops there. Okay, so here's the distribution. First question, what % of 5th graders eventually finished 12th grade? So graduated high school. What they call this X, yeah. Okay, and we'll see that right there, 0.752. Okay. Question B, check that this is a legitimate discrete probability distribution. So again, all values are between 0 and 1, and now find the sum. And sure enough, the sum is exactly 1, so it is a legitimate discrete probability distribution. All right, next question. Find the probability that x is greater than or equal to 6. Okay. So we could add up all of those entries, or we could again do the complement 1 minus those 2 entries. Right, which is probably easier. Okay. So that's the way I would do it. That's a little bit quicker, in my opinion, at least. It's about there it is. About 98% of students finish 6th grade. Okay, letter D. What's the probability x is greater than 6? Okay. So that means they've completed 7, 8, 9, 10, 11, or 12. Again, I could add all those up. Or I'll just take the last the last answer and subtract 0.007 from it. Oops, sorry about that. So there we go. Okay, letter E. What values of x make up the event the student completed at least 1 year of high school? At least 1 year of high school would mean x is greater than or equal to 9. What's the probability of this event? Okay, so that's the sum of 9, 10, 11, 12. Again, we could do the complement, but in this case, I'm looking at the complement versus just calculating it directly, and I'm going to calculate it directly. I'm add fewer numbers that way. So let's see. And we get 93.1%. And there you go. Most students find these problems pretty easy, so hopefully you do too. All right, next question over here. Okay, so you're gonna do a simple random sample of 3 students, and these 3 students will form an advisory board to represent student opinion. Okay, suppose 40% of all students oppose the use of student fees to fund student interest groups, and that the opinions of the 3 students on the board are independent. Okay, that's important to know. The probability is 0.4 that each opposes the funding of interest groups. All right, letter A, call the 3 students A, B, and C. What's the probability that A and B support funding and C opposes it? So we want to find the probability. 40% oppose. Okay, so hold on, let me start over. Let A equal person A supports B, person B supports C, person C supports, right? Okay. All right. And that, oh, this would be the complement, right? They're saying 40% opposed. So this is 0.6 probabilities. All right, now let's answer the question. What's the probability A and B support and C opposes? So probability A and B support and C opposes. Okay, they told me I have independence, so I don't have to worry about conditional. So I can simply multiply. Okay, A is 0.6, B also 0.6, C we want to oppose, so that is 0.4. And we get about 14%, 14.4% to be exact. Okay. All right, part B, list all possible combinations of opinions that can be held by students A, B, and C. And they were kind to tell you there's 8 possibilities. Then give the probability of each of these outcomes. Note they are not equally likely. Good. All right, how about a tree diagram? This seems like a good spot for a tree diagram. Okay, and then each branch. Okay, and now to get the probabilities, you have to, of course, multiply down the branches. So I'll write the, maybe I should write the outcome. This is A intersect B intersect C. So this is everyone supporting, and that's going to be 21.6. A, B, so this one is A intersect B intersect C. Complement. That's what we, oh yeah, we just found that. That's 0.14 or 0.11, 0.144. Okay, A not B, C. Okay, A, not B, not C. So this is going to be a little bit less. Okay, that's 0.6 times 0.4 squared. Okay, let's see. This one is not A, B, and C. Not A, B, not C. Okay, not A, not B, C. Okay, and then our least likely outcome down here, all three opposing. And that's going to be 0.4 cubed. And there we go. There is our tree diagram, which helped guide us to 1, 2, 3, 4, 5, 6, 7, 8 outcomes. And you can see, yeah, they're not all equally likely because each outcome wasn't assigned a 50-50 chance. They were actually each assigned a 60-40 chance. So outcomes up here are the most likely because that's all 60%, and then down here is our least likely, all 40%. But this is where a tree diagram is pretty darn useful, as you can see. All right. Let the random variable x be the number of student representatives who oppose the funding of interest groups. Give the probability distribution of x. Okay, so the number who oppose. What was this? Letter C. Okay, so we could go anywhere from 0 all the way up to 3. Okay, so 0, this was opposing, right? Yeah, 0 opposing is right here, 0.216. Okay, I'm going to jump over to 3 opposing because that's this one right here. That's easy. Okay, but now you'll notice that these other entries occur in more than one location, right? This is the whole idea, again, of combinations. There's different combinations where exactly one person opposes, namely anything that has just one complement, that one, and that one. So you can see there's 3 different ways that one of the 3 opposes, and each is equally likely. So you can just do 0.144 times 3, and that is 43.2. Oops. Okay. And then we can do the same for 2 people opposing. 2 people opposing is that one, and that one. Again, because there's 3 ways that I could choose 2 out of 3. So that's 0.096 times 3, 0.288. And there you go. So there's our probability distribution for the number of students on our advisory board that oppose funding. Okay. Letter D, express the event a majority of the advisory board opposes funding in terms of X. Well, I have 3 students, so a majority means I need at least 2. Okay, so probability X is greater than or equal to 2. That would mean a majority of them. And find its probability, so that's the sum of these 2. We get 0.352. Okay. All right. Next question. Uniform distribution. Oh, yeah, I think I did a problem just like this in our lesson. So they want me to draw this curve. Okay. And the height is going to have to be 1/2, right? Because the total area has to be exactly 1. Okay. All right, B, use your graph to find the area for y is less than 1. Okay, so 1 would be right here. Less than or equal to 1. But again, this one is a continuous distribution. The previous ones we were doing were discrete, so the or equal to part really mattered. This is continuous, so the or equal to part really doesn't affect your answer in any way. Okay, so that's 1/2 times 1, or 1/2. All right, letter C. Find the probability that y is between 0.5 and 1.3. Okay, so 0.5 is about there. 1.3, about there. Okay, so that rectangle has a height of 1/2 still. From 0.5 to 1.3, that is a width of 0.8. Okay, so we get 0.4 there. Okay, and last one, find the probability that y is greater than or equal to 0.8. It's about there. I guess it should be solid line, but again, doesn't matter on a continuous distribution and all of that area. Okay, again, height of that figure is 1/2. Width is 1.2, right? From 0.8 to +2, that is 1.2 units. And there you go. Okay. Hopefully finding, areas of rectangles is pretty easy for you. All right, next question. The sum of 2 random decimals. Generate 2 random numbers between 0 and 1 and take y to be their sum. Okay, y will be a continuous random variable. It can take any value between 0 and 2. However, certain outcomes are going to be more likely on this. Outcomes closer to 1 are much more likely than getting 2 very low numbers or 2 very large numbers. It's much more common to get 2 numbers in the middle or 1 high and 1 low, right? So they drew the distribution for you right here. So you get this triangle, pretty cool. Height is 1. The base is 2 units, and area of a triangle, right? 1/2 base times height has an area of exactly 1. So I guess I have to write that out there. Yay. We can do area of rectangles and triangles. We're excellent AP students, right? Okay, what's the probability y is less than 1? Okay, and the height there is 1, right? So from there to there, this height of 1. It's hard to show that that height is 1. Okay, so we want this triangle here. Here, I'll go like this, that's 1. So that would, again, be 1/2 base times height. In this case, my base is 1 and my height is 1, so that has an area of 1/2, as it should be. It's half of the figure. All right, letter C. What's the probability that y is less than 0.5? Okay. So again, so there's 1, and here is 0.5, or 1/2. So we want this area here. Okay, so again, it's area of a triangle, 1/2 base times height. So 1/2, my base is 1/2, and my height is 1/2, so that is 1/8. Okay, that's fun. Area of triangles. All right, letter D. Oh, sorry, didn't move the book up. Letter D, use simulation methods to answer questions B and C. Okay. So here's what we'll do. Oh, good. So we need random values between 0 and 1, and then we're going to take their sum. All right, so go math, probability, random number, 0, 1, and let's do 200 of them, stored in list 1. Yeah, I thought that might be a problem. Maybe I just do random and then 200. Cool. All right, now do it again and put it into list 2. Excellent. Now we're going to go to list 3 and define that to be the sum of those lists. Okay. And we now have a simulation with 200 trials. And let's see, let's put these in order. So let's sort them. That'll help. So go to list, sort ascending, list 3. All right. Now, when I scroll down list 3, I can answer the question, okay, what's the probability y is less than 1? Sure enough, we're getting close to 1, and we're getting close to the halfway point. So I got, wow, I got 100 out of 200, or exactly 1/2. So my simulation actually hit the exact theoretical. Remember, that's not going to always be the case. Letter C, what's the probability y is less than 0.5? Okay, go back. And we got 30 out of 200, which I don't believe that's exactly an eighth, right? Yeah, so we're a little off there, right? Because 1/8 is that. But that's to be expected. Again, we are going to see variation in data production, right? That's variance. That's why it's random. If there was no variance, it would not be random. Okay, so that one was fun. And last question here. We were supposed to skip 19, so here we are on number 20. Let's see, an opinion poll asks, an SRS of 1,500 adults, do you happen to jog? Suppose that the true proportion is 15%. Okay, so they're telling you, let's just suppose that's the actual parameter. Okay, and we estimate that by looking at our data, right? And the data would be represented by p hat. That's our statistic. P is the unknown parameter. All right, it turns out that this particular example will follow an approximate normal distribution. Okay, so we can use our normal distribution to answer questions on this. Okay. Okay, so they're telling me I can say it's approximately normal with a mean of 15% and a standard deviation of 0.092. There we go. So now this is no longer really a chapter 7 question. All right, letter A, find the probability that my random proportion from data collection is greater than or equal to 0.16. Okay, so remember, first thing we need to do, get a z-score. Okay, so that's the x value that we're interested in minus the mean of the distribution divided by the standard deviation of the distribution. And we get a z-score of approximately 1.087. Okay. Now, you can use table A. Table A is only accurate to 2 decimal places, so you'd have to look up 1.09 if you want to use table A. Or on your calculator, remember the normal CDF, right? It's under the distribution menu. Distribution menu right there. So I go distribution menu, normal CDF. Now I could enter my z-score and then make my mean 1 and my standard deviation, make my mean 0 and my standard deviation 1, or I can enter the original information. So either way, we'll get the correct answer. I guess I'll demonstrate that. So z-score. Upper bound is infinity, mean 0, standard deviation 1. Okay, now that's going to get me the same answer as if I put in a lower bound of 0.16 and upper bound of infinity, a mean of 0.15, and a standard deviation of 0.0092. Okay. So, let me back up. Doesn't get the exact same answer because that was rounded. Okay, that's why you see a slightly different answer there, right? If I had kept enough decimal places, then these would have matched exactly. All right, letter B. Find the probability between 14 and 16% of my respondents say they jog. Okay, so this is just a center section problem. Again, get your z-scores. That's your work on a free response question. If this is multiple choice, I would just jam it right in the calculator, but this is not multiple choice, so. Okay, so there's my z-scores. And we already did this right there. So I know that it's approximately that. Okay. Again, we can use table A. We look this number up. We look that number up. We subtract those areas, and we have our center section here. since this has been a while. Right, that's what we're finding. So if we look up this number, table A will give me all of that area. Then I look up this number, table A gives me this tail here, subtract the 2, and I'm left with this intersection. Or use our calculator, right? Our calculator is set up to do intersections quite nicely. So lower bound is 0.14, upper bound 0.16, mean is 0.15, standard deviation 0.0092, and voila. A little over 72%. Okay, there we go. That's the end of the problem set. Hopefully that's easy for you. And hopefully you are either prepared for the Chapter 6 test, or you just did the Chapter 6 test and did a great job on it. Thanks for watching.